Crank up with Fritz on the way, perhaps. And we'd like to start on questions that were developed from yesterday's effort. Who has a question? Who has the first question?
Could you start over at the beginning?
Yeah, you can. All right. It's a deal.
Okay.
Let me,
Where's our model, Roy?
it's coming up. Well, from the beginning, and let me give us a summary. I'm glad to do it. From the beginning, the topic of the course is fuel cells and electrochemistry. The notion in the matter of electrochemistry is that you can directly convert an electrochemical potential into electricity and vice versa. You can make electricity do the job of converting, for instance, a compound to its elements by electrolysis or other techniques. Or you can aid a process that needs some energy and needs to reverse an endothermic reaction. You can do so with electricity, electropotential. The Nernst equation, the famous Walther-Nernst equation, is the guide to the weights and measures in that endeavor. You balance the equation, you look at the condition of the reactants, the condition of the products, determine what's appropriate in the Nernst equation, enter the fugacity or the partial pressures or what it takes to do the job with respect to Nernst's observations, and you can predict the future in electrochemistry. That's a major milestone in chemistry that Walther Nernst delivered to us, and we can use it with confidence because through the years it's proved out to be the approach that gives you a quantitative analysis of reactions that are aided or that result in the production of EMF. The fuel cells are devices that work on the production of the EMF side of that equation. If you have an exothermic chemical reaction, you can harness it in a fuel cell to develop electricity. The amount of electricity that you can develop is not limited to the temperature difference of the fuel cell. The fuel cell is not a device that relies upon temperature difference. Heat does play a major role in the way that you may choose to activate the chemicals. Heat may play a major role in the way that you choose to control the mobility of ionic diffusion in the electrolyte or in the semi-permeable membrane. But the device, the overall device, will not be limited to temperature differences as a heat engine is.
I have a question about heat. I was reading the book last night, and it says that as temperature goes up in a process, the voltage output goes down.
In any exothermic process that you're harnessing for energy release, increase the temperature and you'll decrease the produced voltage. That'll be a uniform result. And
then we talk about molten carbonate fuel cells, and yet, you know, we know that. Does it really? I guess it must be dependent on the catalyst and the anodes and cathodes.
The trades that are made between approaches typically are in favor of going with some more heat, a higher operating temperature, and with less catalyst. You can make a lot of reactions run at sufficient speeds to justify the capital investment by aid of catalytic systems. Catalytic additions at the right place in the fuel cell work magic. You can take a piece of plastic and put some catalyst on it and feed it hydrogen on one side and air on the other and have an EMF available that you can tap off with the electrodes, take it to an external load. It seems too good to be true that you can run a room temperature device with the aid of catalysts and accomplish that. If you don't like the cost of the catalysts or having the catalysts around, you can do the same by elevating the temperature and get the activation energy out of the heat that's available in the process. Something that we did not cover well enough regarding thermodynamics are the sub-steps in the overall process that are endothermic compared to the steps that are exothermic. For instance, if you feed a diatomic hydrogen fuel to the anode of a fuel cell, there are a number of steps within the process that are required that are endothermic before you get exothermic results. They're activation steps. One is to break diatomic hydrogen into atomic hydrogen. It takes energy to do so, it's endothermic. You can do so by application of voltage or drop the voltage that's being developed in the cell to accomplish it, or you can do so with heat addition. Another step is the concentration gradient, and in a way it's endothermic also. If you want to get rid of steam that's being formed or water that's being formed, you have to divorce it by capillary function or by surface tension properties that you've arranged, or by heat. If you get it warm enough, it'll develop vapor pressure to have an escape tendency by change of phase. So in that regard, heat is very valuable, and it can be endothermic in the analysis of all the heat exchanges in the process. Concentration gradients also occur at the electronic level when ions are formed on the electrodes or on the catalysts, perhaps in a low temperature fuel cell, and are willing to stay there until you give them some energy to move them away. You have ions there that, for instance, on the anode that are positively charged ions of hydrogen. They will repel more ions of hydrogen and tend to block the way for more hydrogen to come to that surface. So that's a concentration gradient that you have to spend energy to overcome. The expenditure of energy can be heat again, or some voltage. Looking at those small areas, they tend to be microscopic issues in terms of where they occur and how you deal with them in analysis, is very important to the improvement of fuel cell economics. Paying close attention to the size of the places where the triple phase events occur, both on the anode and cathode, pay great dividends. And if you do systems analysis on it, well, you get right around to a pretty good insight to the size of particles to center to make a right-sized capillary for the events that you're trying to promote. And you can look at it from a combined standpoint of building your system for doing these combined tasks, including the heat transfer that's needed into and out of the process when you shift from the endothermic substeps to a exothermic substep in the overall process. Anyway, if you keep those factors in mind and start unraveling the graphs that are shown that delineate the different ways that you lose voltage in a fuel cell, and I'll bring to mind the particular graph that summarizes that. It's on the 127.5, we decided. It's on the back side of 127, and it faces 128. When you really start analyzing what you can do about these issues, you come to some macroscopic and many microscopic opportunities. The macroscopic opportunities are to change the pressure of the oxidant in the fuel, illustratively. Another way to change the slope is to change the purity of the fuel or the oxidant. Going to oxygen compared to air makes a less steep slope. You have a smaller amount of voltage played or given up to the steps of the reaction by going to a more pure or higher vapor pressure maintenance in your operation. Anyway, the heat issue is one that you always do trade studies on, about whether you want to elevate the temperature and what the impact would be on the various components. And then you get into these classes of of study, including the PEMs as a lowest practical temperature in widespread operation type fuel cell for ion exchange. Then you move into the phosphoric acid, and then to molten carbonates, and then to the molten oxides, and then you get into the solid oxides. But there are many other approaches that could be conceived out of the periodic chart of materials, out of elements. You can combine many new compounds and arrange many new cell systems out of the chemical reactions that you can conjure for whatever purposes you may have. We remain, however, very influenced by the fact that we're on a very small blue dot in space that's 70% by surface area at least water. So much of the chemistry that we'd like to run is water chemistry. We'd like to get the fuel from water. We'd like to use the water afterwards that's produced as clean, potable water. And so that brings us again and again to closer examination of systems that can work with hydrogen as the fuel or as a major constituent of the fuel, and as air or oxygen as the oxidant and at least a major constituent of the oxidant. Then you get around to the other issues that we covered yesterday having to do with the maintenance of fuel cell component properties, such as the maintenance of integrity of the PEM material by control of the humidity, by control of the temperature, and by control of the impurities that you feed the system so that you don't blind the catalytic areas or the capillaries. Those are the general overviews, and then we get into specific needs. You know, and then you start boiling it down to what are you going to do when all you need is a few watts of energy and the voltage isn't the right voltage out of a single cell, single unit cell. So, you know, first of all, you do the normal thing, you just increase the area to get the amperage that's needed. But then you come to the question, is it better to invert and produce the voltage out of after cell electronics, or is it better to start stacking them and putting series connections in place to produce the voltage? And then what is the implication in heat generation and heat removal? So those need to be addressed in how you build the electrodes and how you build the flow dividers. Please.
Are you going to go into actually showing us how to build these things?
Let's build one pretty quickly, just after we answer questions.
Great.
Yeah, let's start building them, please.
Are we just totally tied into the PEM cell being the mobile unit, or is there
Well, let's go through.
possibility of some of the others having the...
Let's go through the reasons that it has come to the front in terms of development of recent times. The PEM has come to the front because safety. It's a relatively low temperature system that has many, many hours now in electrolysis applications. It has over 100 million, the PEM has over 100 million life support hours to its credit in generation of oxygen for submarine crews. That's a lot of hours of stable operation that you can point at as doing a very important job of supplying the oxygen out of water under the surface of the ocean to crews that have critical dependence upon its integrity. That's hard to beat. But on the other hand, the most time that's been performed in electricity generation is with a phosphoric acid cell. The phosphoric acid by far exceeds, in terms of fuel cell energy production, electricity production, far exceeds the PEMs. They've also come to the front in proving their service as an economical unit because of their dependability, because of their uptime or availability. They're a hands-down choice, frankly, for converting natural gas and accepting natural gas as a fuel to electricity.
How about other liquid fuels like methane or methanol?
Methanol, sure, it's glad to have it.
That would- What you'd have to have basically for methanol.
For the transport.
Really perfected a way to handle methane in a PEM.
Oh, well, you'd have to clean it up. You'd have to clean up methanol too.
You would have
Yeah.
for phosphoric acid.
Phosphoric acid would take either one of them interchangeably, yeah.
It would just accept it.
Yeah. See,
They do have a fuel processing unit on the front end
they do.
that basically.
How practical is it to get anywhere near weight wise, useful phosphoric portable unit?
Well, look at what the space,
Horsepower that we're looking at, 25
Yeah.
or 50 horse.
well, the space program has made those trade studies very carefully. They've always opted for the lightest weight system. That's,
They're a little bit more conscious on weight than we are.
well, that's true. Well, that's quite true. Granted, they are. I think that there's a major continuing hope for phosphoric acid systems in transportation, especially for heavy equipment.
These
The two buses that they had at SAE they're talking about were both phosphoric acid fuel cells.
The major investment, however, even for buses, has gone towards PEMs.
That's one place I thought there might be a comparative weight analysis factor that might.
Well, I think it gets around to the weight analysis, certainly, but at the same time, it's a trade study of fuel processing.
It just looks like it's a lot cheaper to build that than it is a PEM unit. In my mind, it looks like.
It all depends on how many you build per year and how you equip yourself with tooling. The PEM does lend itself readily to tool up and mass manufacturing techniques, but so does the phosphoric acid system.
You know, internal combustion engine's got a lot of heat to dissipate. I mean,
Sure does.
That should be heat dissipated.
Well, that's a very good point. Fuel cells work in conjunction with heat engines as an excellent example of a hybrid or cascaded heat system. However you wish to say it, you can say it in terms of a cascade of energy. The waste of the heat engine can be the heat source that's adequate to run the phosphoric acid system. And it can also supply startup heat, at least for a PEM system.
Of everything I have seen on automobile, I have never ever seen anyone talk about a concept where they're combining an internal combustion engine with a fuel cell.
Oh, our students have.
But
Yeah,
it
we've-
has not even been discussed because the fuel cell is always seen as a replacement for the internal combustion engine.
Let's look at why that would be a good combination. One reason that it would be a excellent combination is for drivability. You could size the fuel cell for the average load and bolster it with what we've always called upon the piston engine to do, and that's to pick up the turndown ratio that's needed for drivability. So in that regard, you could think of the combination as a way to get more out of the package and drivability analysis. Then you go to the overall life cycle energy consumption and find some advantages in using the regenerative fuel cell as the way that you connect the vehicle during deceleration to your energy storage system. You use the kinetic energy of the vehicle in deceleration to run your fuel cell with regenerative electric motor generators backwards. You run the fuel cell backwards to electrolyze water, save the energy for later use in the fuel cell or for use in the IC engine.
That's the reason I asked a question yesterday about how fast this thing could reverse, because on stop and go traveling, you're talking about 10, 15-second cycles.
True enough. Well, the small cells, that is to say the thin membrane cells, can reverse very rapidly. Please.
Roy, what about the gas turbine hybrid that your research is doing? That high temperature exhaust would be very useful.
Well, that would probably be more in the range of the carbonate systems, if you wanted to match them. But that's a good one, sure. Gas turbines tend to have a much higher temperature exhaust than piston engines, and you might as well think in terms then of the carbonate systems. It is possible to also look at another combination, which would be the solid oxide fuel cell cascading heat to a Stirling engine, or perhaps an advanced Ericsson engine, Ericsson cycle engine. That would be an adequate temperature in the cascading of heat at minimal entropy increase, because you'd minimize the temperature of the exchange. But the reason that you'd like to look carefully at these as competitive trade studies is that out of these trade studies come new opportunities in doing better out of the deployment of resources that we have plenty of, but all of which cost a lot to put into a capital investment of design and energy intensive vehicular powertrain equipment.
We've talked quite a bit about the efficiency of the fuel cell. Is that efficiency fairly uniform when we reverse it into the
Electrolysis? Yeah, the electrolysis can actually be more efficient than the fuel cell operation. Sure. What we found in terms of practical, achievable efficiencies in the electrolysis mode is that some of the things that are very against your interest in the fuel cell are aided by the electrolysis process. Adding heat to the electrolysis process reduces the applied voltage requirement. That can be beneficial, you know, as a point of illustration. You can go directly out of electrolysis to high pressure hydrogen production. If you arrange your system to be a pressure adequate system, that is designed for producing pressure and holding pressure, you can go directly from liquid water to high pressure hydrogen in one step by electrolysis. That's a great advantage and saves a lot in terms of operating efficiency compared to producing low pressure hydrogen and then going through a compressor, and saves in capital equipment investment and quiets the system.
So like, what you're saying then is if I have high pressure water initially, and then whatever that pressure is, say it's 3,000 pounds, when I use electrolysis, I'm going to get 3,000 pound hydrogen and oxygen coming off.
That's correct, or more. If you run it cyclically, you can get more.
Even if you just used like standard pressure of water sitting there, but it was enclosed in a container, once you electrolyzed it, wouldn't it be with that kind of pressure?
Yeah, two different cases were brought on the front row. The two different cases were continuous operation where you put in 3,000 psi water and get out 3,000 psi oxygen and hydrogen. That's good. This case was intermittent, where you take room temperature, room pressure water, put it in an electrolyzer, close it with a pressure seal, produce whatever pressure you choose at the regulator that controls it. And then when it's empty, you have your choice. You can use up the reservoir of oxygen and hydrogen to ambient conditions, that is to say, use it up with respect to its temperature and pressure that are available for doing work, then recycle or re-add the water to the container, seal it again, and cycle again. Two good ways.
Does the Hamilton Standard Unit, as it's used as a fuel cell, it actually separates the water outside the unit somehow?
No, well, it does a reverse osmosis cleanup.
Does the reverse osmosis cleanup?
Yeah, well, the preferred art in that is to you start with seawater.
But on the Hamilton Standard deal where it goes back and forth, you don't have to.
Oh, yes, that's correct. Once that water is produced by the fuel cell, it's fine. Yes, that's correct.
Then they just take it apart, put it back together, they have to take it outside the fuel cell element though, don't they?
I see what you said. Yeah, you store it outside the fuel cell element.
Otherwise it would flood.
Yeah.
You keep saying that it's pretty much a no moving part. How do they move it out? Pressure?
Pressure. But your point is a good one from the standpoint of transportation. You still need to attend to those problems in rubber-tired vehicles as much as you do in submarines. You have to make that arrangement. The reason that that technology came to the front for submarine applications is important to remember. It was silent. If you're going to bring this home and have it in the closet, you need it to be a good citizen around the home. Silence is dear. Yeah, it's golden. Please.
My question is kind of oriented around the pressurization process. Now, I realize that as you flow electricity through a resistor, the resistor increases in heat and increases the resistance, right? Where is the resistance in the pressurization in hydrogen? Is it electrical resistance or is it...
Really good question. Did everybody catch the question? The question is, in the electrolysis process, where do you develop the resistance? And the answer is the pressure itself makes more voltage requirement for the separation. In order to make the current flow in the electrolyte, whatever the electrolyte may be, you have to apply more voltage as pressure is produced.
Okay.
However...
If I wanted to pressurize it into liquid hydrogen, theoretically, this is theoretically,
yeah,
I would have to increase voltage.
you would. But just keep in mind this. Hydrogen has a very low temperature triple point, above which you will not have liquid, no matter how much pressure. You can have compact gaseous hydrogen, but not liquid.
You cannot achieve a liquid.
You can't, but you get rid of its critical pressure.
Roy?
Yeah, you have to...
Pressure, more advantages. If the more pressure you have more voltage you'll get out of it.
Well, that's true. Both on the that is a fact. That happens to be a fact both on the fuel cell and electrolyzer condition. You can maintain a higher operating voltage by increasing the pressure of the hydrogen and by increasing the pressure of the oxygen, for instance.
So if you had it in a closed container
And
went along, you would need less voltage to separate water and hydrogen.
let me just finish this one and then we'll pick this up. But it's also true for a different reason that increasing the pressure of produced oxygen and hydrogen by electrolysis of water requires higher voltage. Offsetting that, and this is an important observation, offsetting that is that the more pressure you have, the more you may aid the physical proximity, the production of contact where it's needed on the catalyst. Catalyst makes smaller bubbles. Bubbles interfere with access to the catalyst. Pressurizing them gets them out of the way to interfere less.
You're saying higher pressure electrolysis requires higher voltage.
It does.
There's a happy medium there someplace you have to find.
Well, it's a straight, it's analysis. You go back just to what Walter was mentioning. You decide how much weight will be incurred by design changes, and you consider them in competitive analysis to see what does the most for you. You look at combinations of weight, cost, efficiency, longevity, and you balance, as engineers will, these compromises in your formula. And the next question.
I think you answered it.
Okay.
Like you said.
Repeat it and let's see if we got it.
I was saying, if you did use like a closed container that created its own pressure, it would take more voltage as the process went along. But then again,
It does.
the pressure would also make it a little more efficient.
That's true. The question again went to pressure. Is pressure going to hurt you or help you in electrolysis? It requires more voltage, so that would seem to hurt you, but it certainly is a lesser of evils compared to buying a compressor that you use outside the unit. And it's certainly, in terms of being quieter and less expensive, of great advantage to just add voltage.
Now, can I do that automatically and just go on vacation? And I got, in essence, a perpetual motion machine there?
You don't have a perpetual motion machine.
You know, shut itself down automatically.
But does it enhance it to an equal trade-off about pressure and voltage?
Yes, it does. You're generally speaking much better off
It's actually better.
increasing the pressure of electrolysis in terms of making a compact machine.
Are you talking about tens of volts or hundreds of volts?
Yeah,
You gotta
linear.
go to?
1 volt.
Well, that's
Yeah,
temperature, but
not much. Well, pressure and temperature. You can look right at the Nernst equation and decide how much of it you can stand. It won't be very much voltage you'll add to develop the pressure. Please.
Okay, so I have some PV panels and a hydrogen wind electrolyzer. Can I hook that directly to, say, a propane tank? And will that charge the tank up to, say, 60 psi? And then what happens? If I just let it go and didn't touch it, would it explode the tank at some point or explode the electrolyzer? Or would it just sort of shut down at a certain pressure? Or should I have a pressure gauge in there and shut it off at, say, 60 psi?
Practically speaking. Yeah, the answer is, practically speaking, in order to succeed in this endeavor that you have described the possibilities of, here's what needs to be done. We need to check the viability of each of the components that you've mentioned.
Okay.
We need to do a safety analysis on how to check the pressure viability of the electrolyzer, and then provide and of the receiver and of the tank, and then provide a fail-safe system that has a large safety factor built in to not violate that viability. That can be a combination of things. You can do a voltage check and make sure that you don't apply more voltage than would develop a certain pressure that you decide is the safe pressure. You can bolster that with a pressure relief system, a pressure regulator, and you can further bolster that with some strain gauges on structure and make sure that you don't pass the structural capability of your weakest link, whatever that may be. You can furthermore make some safe blowouts. You can make some places that are safety blowouts so that when, and you absolutely as a designer assume that it's going to fail, but when it fails, you're going to make it fail to a prescribed place that you prefer.
this has that electrolyzer is like an open air electrolyzer. Doesn't that, in order to really charge a tank, doesn't this electrolyzer need to have a pressure vessel to begin with?
Or be built as a pressure containing vessel.
Right.
Correct. One way to do that is to make the places where pressure exists small dimension places. You can arrest pressure very locally, that's a good thing to do. Or you can make it general, where you put the whole system within a pressure containing atmosphere. Both approaches have merit. But in the trade studies, you make those as a competitive analysis of what does the most for you. Then finally, and let me emphasize this, finally you want to make something that is field serviceable. You want to make it so that it's not only a safe, fail-safe, and when it fails it's to a preferred place that's also safe, but you also furthermore want to make a readily maintained system that the conditions of operation are conducive to promoting. You want to make systems so that they're accessible, so that they tattletale if possible, that they're getting weak before they fail, and that they do the most for you design-wise for facilitating human intervention for a profitable outcome, safe and profitable outcome. Anyway, a lot of words to say. You can go about your design stepwise and come up with a excellent result if you just bear in mind that you're going to test the components, put a safety margin in, and make subsystems that never let you get to those limits that you've set for yourself that are far below failure.
Now,
But-
how do you test the systems?
Well, hydrostatically, you put water in them and apply pump pressure to do a hydrostatic test. You'd typically like to do fatigue cycling on your hydrostatic tests that far exceed the practical life use of the device. For instance, if you're going to store fuel, if you're going to store hydrogen, a good rule of thumb is that you cycle 100,000 times. This is going to be a lot more than they'll cycle in real life for the usual size of hydrogen that you store for fuel applications. So you pressure them up and depressure 100,000 times. And then you write the analysis of what that would do for you in field life. It ought to be 25 times around the world or something like that. Something way beyond what will really happen. And then you say, well, what if I superimpose ketchup or something that's going to come into contact as I go through McDonald's? You put all the superimposed degradants that you can think of on top of those fatigue cycles and do it again. And you put it in concentrated sunlight. Well, anyway, you go through these and you find out how to make it fail. The test fails if it doesn't make your product fail, because you want to know how it fails. But you also want to know how to succeed in the real life that it's going to experience without question. Then finally, you make it compatible for recycling. You make that design so that it's readily recovered and put into a further life after you're done with it, first time through.
Now, if you go out though and acquire components, commercial components, they theoretically have gone through all this testing. If they're rated for a certain amount, then can't you feel confident that you'll be okay at that certain amount of pressure?
No. Here's the reason why. I mean, this is an important reason. If you mentioned propane, when you go from propane to CNG or hydrogen or some other fluid storage that doesn't have a triple point in the ambient that you're running, propane can be liquefied just by pressure at the ambient conditions that people like to exist. Hydrogen won't be.
It's impossible to liquidate.
You can make it very compact as a gas, but it will not be liquid in properties. The reason I bring this up is that propane has different characteristics that tank will be designed to accommodate than natural gas or landfill gas or producer gas or hydrogen. So you have to make sure that your tests really take into account these different properties. After you've done the hydrostatic test, you do these chemical compatibility tests and decide if you have some peculiar property of the real fluid that you're going to expose the tank to that would degrade it. And you do accelerated studies again.
Yeah, you know, though it seems like you need a lab to do all the studies. The average person doesn't have access to all this hardware.
No, but here's the deal. Take the Wright brothers as a example. They didn't have much of what we consider to be necessary in today's standards. Did it stop them? Not at all. They overcame one after another of what many would have considered to be deal stoppers to their goal of flying through the air with a engine-powered aircraft. We don't have to do as much as they did to succeed in this endeavor. And what I'm saying is that almost any place that people practice a lifestyle that North America's familiar with can do these things. You can arrange pump and testing and get a hold of some cycle counters and find out how many it went until it broke, and not hard to do.
I can testify to all that.
One big difference.
I can testify to all that.
EPA today, they didn't have to test.
That's true. That's,
Big dog.
yeah, the big dog, big difference. Jack?
Well, as I'm sitting out there in my little retreat generating hydrogen, compressing it, the only thing I have to add is water, as I use the water up and produce hydrogen. Now, do I have to fight that pressure of the hydrogen to add my water?
Yes. Oh, yeah. Well,
I have to fight that.
you have to decide, as I understand it, your example is you're going to use photovoltaic electricity and you want to make stored hydrogen out of water using that electricity. Yes, you do. You have to run one of two ways. You have to run cyclically, where you fill at ambient pressure, pressurize as you create gas by electrolysis, run to the end of your water reserve or to a point that you determine that your amperage isn't adequate, stop, use up the products that you've made until they're all gone in pressure.
Turn a valve, so to speak.
Turn a valve, so to speak. Refill your system and start over. That's fair.
A little bit of water goes an awfully long way. If you have, say, 5-gallon electrolysis, couldn't you put a 1-gallon add-on to it with 2 valves? Open one valve, let it drain in, close the valve.
Yeah, sure.
The first valve, you would lose 1 gallon of the pressure, but
Yeah, I see.
I mean, you can feed water to it in a batch.
How does Hamilton Standard get through?
Both ways.
Both ways? Or do they have a cycle in hand?
Well, it's more preferred for silent running that you use a very quiet pump to just maintain pressure. You never blow down at silent.
They do have a pump in that unit?
Yeah.
Hydrogen pressure activated pump?
Well, it is. You maintain a pressure.
Or is there
At a-
electricity hooked to it?
Both. Both. Please.
Boy, I can understand your seawater thing with potable water, where seawater is always available. But we took that same fuel cell and put it on an automobile to recycle the water. Can you diagram what our problem is?
Well, it's, as Walter said, once you get out of the notion that you're going to exhaust one of the two components that you produce, but if you're going to save them and use them again, then you'd do a different thing. You'd take an inventory of water, add that to your electrolyzer, produce at least hydrogen, use the hydrogen, for instance, in a fuel cell, collect the exhaust from the fuel cell and not incur strange water, not incur additional water, except on maintenance periods. You know,
You're going to get the voltage for your electrolysis in a automobile situation.
well, for instance, this would be a sum of a number of options that you can exercise. One would be stopping or regeneration. Energy. You turn your traction system into a generator, and you use it in the period that you're converting kinetic energy to electromotive energy for this chemical storage purpose. And that's a very good thing to use it, apply it to. Another source of electricity that you may choose to use is from another prime mover, such as an engine that you have on board the system. You may want to run an engine at a constant best condition, and any surplus from your propulsion system is added to this system. So it's interchangeably used with stopping energy. Or you may want to run this intermittently. Jack's going to do a lot of intermittent operation. What he's going to do is to plug this in at home. He's going to take cheap electricity at night, or sometime when he's relaxing, build up his store of hydrogen, run the system, but retain the water out of his system. So he has a choice. He can do it either way. But in this diagram, he's retained the water. And the next night, he's going to re-electrolyze it. But this would show, in his case, running on fuel cell as the energy for his golf cart, and using the stopping energy when he's going down a long hill on his golf cart as part of his input to that regenerative operation during the time that he's mobile. But it's perfectly fair to run this off of his PV or wind or Palo Verde power plant. Whatever he decides he wants to do, he can plug that in and use it.
I have one other quick if I'm going to convince my wife to drive with hydrogen in her car, I'm going to throw a question at you that she'll probably throw at me. Hypothetically, when the Hindenburg blew up, if those gas bags were full of propane instead of hydrogen, what would have been the difference in survival of the people in the Hindenburg, if any?
Well, if you had a heavier than air substance that was flammable in the Hindenburg disaster, you'd have had many more deaths.
Because the heat would have went down instead of rising with the hydrogen.
The heat source would have gone where the people went.
How about the impact of the explosion?
Well, get the video out for the wife. Get the video out and see what happened. In the video, you can count the time, count the seconds that it took for the hydrogen to escape. 7.2 million cubic feet of hydrogen escaped in less than a minute. It went up. You can.
Was that in 1936?
37.
37. Yeah, I remember I was 13 or 14 years old when that blew up.
But don't these studies show that more people died from the diesel that was in the power propulsion?
Most of the deaths on the Hindenburg disaster were due to impact. People jumped out, fell out, and were injured on the ground collision. 2 people, in the morgue reports, 2 people were pronounced dead because of burns.
Okay.
2. The time of disaster analysis, both in this country and in Germany, determined that the Hindenburg burned because the fire started in the surface of the Hindenburg. Afterwards, much exhaustive testing has been done. Addison Bain, a member of the American Hydrogen Association, has devoted a lot of his life to this. He's a retired now NASA official, and he's made a major, careful scientific analysis of the fire disaster of the Hindenburg. Number one, what Bain's work verified were the German engineers' reports that said that the Hindenburg would have crashed and burned, or burned and crashed, regardless if it had helium or hydrogen as a lifting gas. It could have had an inert lifting gas and had the same result. The reason is that the fire that initiated the disaster started in the skin due to static electricity discharge that kindled sustained fire or sustained combustion in aluminum powder that had been selected as the colorant for the varnish that was in the skin of the Hindenburg.
Outside skin?
Outside skin.
No kidding.
They've taken original fabric samples, subjected them to the same static discharge that would have existed in 1937 and produced the fire again. Then they took the formula for producing the skin, reproduced it, built new skin, subjected it to the same discharge, same result, spontaneous fire.
That wasn't aluminum skin, that was a cloth skin, wasn't it?
It was a elastomeric skin that was filled with aluminum powder so that it would look to ground observers or anybody else that was a casual observer like this was a big aluminum airship. It was truly a rather remarkably light composite, but they wanted it to look strong and heavy. So they chose aluminum so it would look like the advanced aircraft of the day as a shiny aluminum, big, 813 feet long, dirigible that could fly longer, had greater time aloft than anything else by far. Any other aircraft would have been out of the sky long before the Hindenburg barely got started. They could go all the way from Berlin to Rio de Janeiro and back if they decided, without stopping.
What caused that static that particular moment? Why didn't it go earlier? Well, what caused that static? Were there atmospheric conditions?
They came to New York in a thunderstorm and
Oh, okay.
were waved off. They decided they couldn't land because it was too severe. It didn't get less severe, they just changed places to have the disaster.
Well,
They went,
through thunderstorms before, though.
well, they did, but not under this condition. They dropped a line, they made a ground so that
Oh, I see.
the Hindenburg became the antenna at altitude that was ready for anything in the sky that was at potential compared to ground.
When they drop the line is when they make the contact, they make this complete circuit.
The first people that knew this were the German engineers aboard that aircraft. They didn't miss it, and they wrote it. But much propaganda flowed, and we're the subject of much propaganda about the Hindenburg. First of all, we dearly didn't like it, because here were swastikas on the empennage flying over Philadelphia or Boston or New York or any place they chose with their propaganda machine saying that the Third Reich was the only way. Well, we didn't think so. There was much advantage taken in terms of propaganda exchange when the Hindenburg disaster happened. We said, well, anything those guys are doing is no good. And it was dumb. They were dumb to use hydrogen to serve as a lifting gas. It was dumb. But it had been working for 37 years. They had a pretty good license for staying dumb. But that wasn't what caused the disaster.
I see. Well, as the windows were windows blown out in the near vicinity or anything from the explosion?
No. In fact, if you look at the reports of the day and look at the video yourself, look at the film footage, the actual film footage, it was a quiet fire.
Now, if propane had been in those bags somehow, what would have been a different story from the explosion, then, wouldn't it?
Oh, I doubt it. I think that what would have happened was...
I'm not saying the word explosion, there was no explosion.
That's
what
true.
I'm saying, but if there were propane in those hydrogen bags instead of
Would have
hydrogen...
been a disaster because never would have gotten off the ground.
That's true.
Well, that's I'm not getting into the dynamics. But with the explosion, this,
What Mr. Harris is saying is that in a container that contains only hydrogen, the entire contents are only the fuel. Nothing happens inside, whether or not you put sparks or arcs or hot punks or anything in there, nothing's going to happen until it has the oxidant to sustain chemical reaction and release more heat. No question on that part. In order for there to have been an explosion on the Hindenburg, you'd first have to have transferred into the lifting bags air or oxygen or some other oxidant. That didn't happen. You can watch and see that the fire didn't occur until it got out of those bags and mixed with air.
Another way to explain that would be when you ignite that deal right there in the front, it doesn't travel back through that line and into the tank. There's no air in there.
Well, that's a very good point.
See, so it's the same thing. The fire can't go in there and burn because there's no air in it. If it could burn, it'd go back that line and in that tank and blow it up.
And you...
One way down there?
No.
No, just the pressure keeps it
But-
on.
See, if that fire could travel back in there.
But you need the combination of mixing with fuel and oxidant and ignition. You need a way to get ignition.
If you put a match there, will that burn?
Sure.
Sucking air, getting there.
Because you got
Absent,
in here, I see.
absent the mixture that is a chain reaction sustaining mixture, ignition, and continuing supply, and the absence of a heat sink that steals the heat that would have supplied the adequate activation energy, it quits.
I probably asked my question wrong. What if propane were in the bags?
Don't
instead
say the word explosion.
of- I won't. I won't.
It could have burned on the surface. That's
On the
all
surface,
that
initially, the air got into the propane quicker because of outward oxygen, quicker than the hydrogen, because the hydrogen rows.
Well, let me just say, if you want to build a bomb, the Hindenburg wasn't the way to do it. That was not a good approach. I mean, that was that was the wrong approach. If you want to build a bomb, what you need to do is to build the oxidant and the fuel together.
Right.
And you need to build them so that they're not going to be quenched. You need to build them so that they're isolated from quenching, because if the heat is taken away, they quit. That's why you put water on a fire. The other thing about building a bomb is that the fuel and oxidant need a lot of intimate availability to each other. If you have a chunk of fuel in one end and a chunk of oxidant in the other, there's only going to be a little interface that has a chance to do something. So you need to intimately bring them together.
Roy, under what circumstances will hydrogen spontaneously combust?
Hydrogen will spontaneously combust if you pre-mix it with the oxidant. You pre-mix it, get it intimately mixed up, absent a heat sink that stops the reaction, and that you initiate, you do the activation energy that we've looked at in fuel cells, you initiate the process. Otherwise, it doesn't do it. You can gladly put the oxygen in that tank, leave it 1,000 years, absent activation energy.
What is the upper and lower explosive limits of hydrogen?
4 and 74. Hydrogen holds some world's records. It is available for combustion in a wider air-fuel range than virtually every other fuel.
For acetylene.
So Roy, technically speaking, if you have that full of hydrogen, and assuming you put a spark in there, that thing wouldn't blow up because the spark wouldn't do nothing to that hydrogen, am I correct?
That's correct.
Because there's no oxygen.
That's correct. Unless you had an oxidant or a supply of feeding it with the spark.
As opposed to diesel, which, well.
No, yeah. You're worse off, I might just say this, you're worse off if you had a tank full of the monomer tetrafluoroethylene. The tank of tetrafluoroethylene, which can be made into Teflon, which we consider to be a very inert substance, in its state as a monomer is much more dangerous. It's a mono explosive. It'll give up a lot of energy as it polymerizes. You can make a one component, a mono substance device for releasing a lot of energy, blowing up, out of something that's going to produce something as tame as Teflon. And in that case, you do not have to have the oxidant in the fuel. But if you have, by our definition, by the common use of the term, fuel only, the activation of the fuel doesn't get the job done and if you want to produce an explosive.
Nitroglycerin is kind of another example.
Nitroglycerin is a mono explosive. It does it by itself. There are a number of them. You can do a yeoman's job of blowing things up with black powder that you can produce.
I see.
And so forth. But among the fuels that require oxidants, all you have to do is keep them separate, and you can store one or the other without fear of sparks, arcs, and hot spots. Please.
Where does the activation energy come from, like mineral spirits?
Well, here's a different implication. You're thinking of spontaneous combustion? Well, in spontaneous combustion of oily rags, mineral spirits and what have you, what happens is that you get a slow chemical union that develops to a critical mass of heating to a very fast chemical union, and it breaks out in flame. And it also may be necessary in that case to put a chimney effect in place so it can get more air.
Roy, on that subject, then, what is the common misconception or myth of liquid hydrogen?
Well, there are a number, but I think your question implies blow up. Regarding blow up, if you have liquid hydrogen and add heat, it'll make pressure. It'll want to occupy more space as a heated condition than its cooled condition. The result is that you develop pressure and you can exceed the viability of the container and blow it up, break it. The rate at which you add heat determines the rate at which you can expand it and create the explosive appearance of the failure. But there's still another implication, and that is that cold substances produce material changes from ductile to brittle in nature that are conducive to failures. And some materials that you might use at ambient temperature for propane storage become very inappropriate for cold storage of liquid hydrogen. Things that are good are face-centered cubic materials such as aluminum and stainless steel, non-magnetic stainless steel. Things that are not good are body-centered cubic structures like magnetic steel, as a rule of thumb. Okay, we're due for a break. Bring more questions after.
Now adding distilled